My name is Faizan Ahmed, and I am a medical physicist and radiation protection officer at Yagat National Hospital, Karachi. And the topic of today's presentation is estimation of the external exposure from the patients which are undergoing nuclear medicine diagnostic tests. It is basically a research-based project which was performed at our facility, and I will be sharing with you the findings of that research. So these are the contents for my presentation. Regarding to the nuclear medicine, as we all have some basics related to radiology, so I am skipping that part. Nuclear medicine basically tells us about the physiological imaging. That means anatomical imaging is not done in it. It's basically regarding to the functional imaging. The basic procedure for nuclear medicine test is that we inject the nuclear medicine in the patient. So it's typically the radioactive isotope which is used for as a tracer, and this radioactive isotope is usually the technetium. Technetium, why only technetium? Because it has some characteristics which are very favored in case of diagnostic tests. First of all, it has short half-life and it emits gamma rays, and it can be labeled with many other pharmaceuticals. Its average energy is 140.5 keV, or you can say 140 keV. So regarding to our research, that after the injection to the patient, that means that radioactive medicine has been administered to the patient, what will be the dose rates outside the patient? Because whenever we inject it to the patient becomes the radioactive source. So how much will be the dose rates surrounding the patient? How much will be the dose rate at the surface of the patient? And can we estimate some dose rates for the future, means for the future time after 1 hour, after 2 hours, so that the accompanied people, that means that staff coming with the patient or the other attendants coming with doses, so how much doses they will get, we want to inquire it in this research. So the methodology we have taken here is that we have taken the readings, the dose rates, in two circumstances. Number one is dose rates from an unshielded technetium-99m source, only the source, not the patient. And then the dose rates were taken from the radiopharmaceutical injected patient. That means now patient is the source of radiation. And by these readings, we have made an empirical model regarding to all the settings, all the injected activities we have performed in this research. So the experimental setup for the measurement of the unshielded technetium-99m source, the dose rates were taken by using two survey meters, just like this. There is a radioactive source in the center, and at some distances we have taken the readings by two survey meters. Both of the survey meters have these specifications, as you can see it here. Both are compatible with the energy of this technetium-99m source. We have taken the many distances, we have taken the readings at many distances from zero, that means at the surface, to almost 2 meters, that is 200 centimeters. And related to the activity, we have taken it from 5 MCI, we have taken it from the 0.173 MCI, 0.5, and up to so on, gone to 53.177. These numbers are arbitrary, but all the MCIs are related with the diagnostic tests. The usually used diagnostic MCIs are in these readings. Now, regarding to the patient, we have taken the readings from the patients as well for some diagnostic tests, that is myocardial perfusion imaging, whole body scanning, renal scanning, thyroid, and other tests, some other tests as well. So for taking the reading for the case of surface, at the surface of the patient, we have given the OSLD, the dosimeter, to the patient. The properties of OSLD or the specs of OSLD are written here. It's made of aluminum oxide. It is typically employed in almost medical centers for the dosimetry of the workers. And furthermore, we have taken some readings away from the patient as well at two distances, 60 centimeters and at 100 centimeters. These readings were also taken from that two survey meters which I have shown you earlier. Now, regarding to those who work in the nuclear medicine, they must be familiar with these doses. Typically, these are the radioactive doses, or you can say the radioactive medicine activity injected to the patient in these tests, which we have performed during this study. These are the number of patients or number of samples which we have taken the data. And also, we had done one more thing, that is usually the radioactive model, the radioactive source model is taken to be the point source model, and patient is not a point, right? Patient is a kind of line. So we have taken these models into account as well. This is the equation for point source model, and this will be the equation for line source model. So we have taken the values, the dose rates were also calculated by using these two models as well. These are the equations you can see at some later time. These are present in many reports as well. So as assumption was performed here, that means the patient is a radioactive source, but it is a kind of shielded source. It will have dose rates as compared to the unshielded source, it will have dose rates lower than that. And we have taken these readings as well and compared it with the technetium-99m source, which was unshielded, and attenuation factors were calculated by using these values. For the attenuation factors, we have simply performed this division, that is the dose rates at patient surface divided by the dose rate at that source surface. Similarly, at the given distances, we have taken the dose rates in these ratios, and we have that attenuation factor. So this enabled us to make the empirical model. That means related to the dose rates and the distances, we have made a model. We already had the model for unshielded technetium sources, but we do not have the model for the patient. So we have implied these attenuation factors into our model to make it for the patient as well. And for that reason, we have used bilinear interpolation, because we have two axes. You can say we have two axes. One is the MCI, that is the dose rate, that is the doses activity, and the other one is the distance. And related to the patient, when it comes for the patient, we have taken the attenuation factors. We have multiplied the attenuation factor for the reading for the dose rates outcome of the injected patient. So what were the results? The results are quite similar as compared to the texts for the technetium-99m source. These were the results for some activities. We have many readings. I cannot show all the readings here. I'm showing only some readings here, and these are totally comparable with the dose, with the point source model and the line source model as well. Okay, so those who have seen these kinds of graphs, this is basically inverse square law. This is following the inverse square law. It is for the unshielded technetium-99m source. These are some more readings. Now, related to the patient, first of all, these all readings are comparable with the line source and the point source model as well. And at near the source, the readings were more deviating. And when we have taken the readings away from the source, the readings were quite similar to both of the survey meters. This is the comparison of dose rates by the survey meters and the line source and point source model. And as you can see here, as we go away from the source, the line source and point source models are really comparable. And similarly, the dose rates from the survey meters are also comparable. Near the source, we have very much deviations in the dose rates. These are some readings for the activities. Now, regarding to this measurement, the conclusion is that when we are away from the source, basically The point and line source model give almost same reading, because when we are away from the source, it's not the line, it's the point. But near the source, we have to perform measurements because this is only source. Now talking about the patient, what will be happen to the patient, or in the case of patient? So for that we have readings. These are the readings and all the time spent during that time in the department. These were the doses which were measured by that OSLD, by that dosimeters. So we have calculated the dose rates, the average dose rates from this, and compare it with the average dose rates of the survey meters. And as you can see here, survey meters were giving high reading as for the unshielded source, and for the patient the dose rates are very low because patient is a kind of shielded source. So these are the findings for the readings. As you can see here, larger the activity, larger will be the dose at patient surface. Highest number is 0.74 MSV, and the activity injected was 27.91. This is for the MPS test. This test is done in 2 phases. So readings from the radioactive source gives one information, and that is quite possible. That means we have the reading, that means the activity, highest the activity, higher will be the radiation dose received by the patient. Typically these are not employed in the clinical setting because the release criteria for technetium 99M found by the NCRP report 155 and US NRC is 760 MCI. And regarding to the 760 MCI, no diagnostic test is performed at this activity. The diagnostic tests are performed for 30 MCI, for 20 MCI. We do not give 760 MCI to any patient for the diagnostic test. So this is not related with the release criteria, but related with the radiation doses outside the patient. So higher the activity injected, higher will be the radiation dose, the cumulative dose of the patient. And obviously the dose rates were very much lower than the patient release criteria. So these are the readings at some distance at 60 centimeter from the patient, and you can compare it here, the point source model and the line source model giving the almost nearly same reading, and for the patient the readings are much lower. Again, this is implying that the patient is a shielded source. These are the comparisons of the point source model and line source model and the reading which were taken at the patient. Now, one more thing is that the point source model always overestimates the dose rate. Highest reading for the point source model in every graph. Similarly, these were taken at 100 centimeters from the patient, and now the readings are much more comparable to the point source and the line source model. Right, as you can see here, the readings are much more comparable because as we go away from the patient, as we go away from the source, it becomes a kind of point source. But point source model always overestimates the readings. So these readings were taken from the patient, and patient was considered to be a shielded radiation source, and it was found to be the true one. And related to these readings, we have made an empirical model. That means which values I have shown to you, the ratios which I have shown to you, these were employed for the patients. This is our empirical model. It works for that distances which we have taken and the MCIs for which we have taken. We can convert it into many units. Just for the reference, we have put here the values, the screenshots. And these were also implied regarding to the test, because in each and every test the distribution of the radioactive source inside the patient is not same. So the dose rates coming outside the patient will not be the same. So some comparisons related to published study previously. You can see here the maximum doses to the companion. In this study, they have given the radiation dosimeters to the companions, and companions were with the patient all the time, as they have stated in their papers. So these were the readings, and if similar conditions were employed in our empirical model, these were the readings. Right? It's very much near for some cases, but too far away, but too much deviated for some cases as well. This is again for another study, and these were the cumulative doses found out for the bone scan, and by our model for similar scenarios, we have given the readings, we were taking the readings, and it's quite similar for case of bone scan. This is another study. As you can see here, some readings are quite similar, but others too much deviated. So what we can conclude with it, that means the technetium-99m radiation, the technetium-99m source has been injected to the patient, and patient becomes a radioactive source. This radioactive source obviously gives dose rates outside it, and it will be received by the companions, by all the staff which will be interacting with the patient. Now, the highest doses were found to be the MPS test, and the lowest doses were found to be for the renal imaging scan. Published articles, to some extent, the readings were comparable with our empirical model as well, and the point source model, which we usually take because of its ease, it highly overestimates the dose rates from the patient as well. And moreover, any of the tests did not give this dose rate, did not give that dose rate which related with the patient release criteria. These were all lower than the patient release criteria and well below the regulatory guidelines as well for the caretakers. So furthermore, the empirical model and what we have made here, empirical model will always be helpful, and we can find the dose rates to the companion or the doses, cumulative doses to the companion if we put right conditions in that empirical model. The studies which were performed earlier, they do not give the exact scenario. They do not give the exact scenario of their diagnostic test. So that's why some of the readings were taken as average, or some of the readings were taken as a typical reading. For example, here this distance was not given in this study, so we have taken it to be 30 to 50 centimeter around. So future work, we can make it a more precise study by using other dosimeters, the comparable dosimeter, small size dosimeter, and we can place it on many areas of the patient if we want to have a more accurate reading. But overall, the radiation doses were lower from the patient, but ALARA principle is there, so many of the centers could benefit from it, as they know that how much radiations could be received by the companions or by other staff due to interaction with the patient. And that's all for the presentation. Thanks to all of you. Any questions?
Hello, Faizan.
Yes, sir.
Such a nice study, but just a quick question: any recommendations or any change in your practice in terms of radiation protection for your patients and attendants after such a wonderful study?
Yes, sir. We have basically employed some rules there. That means, if I could say that, usually the patient, this is a typical practice that no companion are usually with the patient after the radioactive medicine were injected with the patient, but we take it on a strict notes as well. Means we have employed all the basically warning signs were there, but warning related to this as well for the companions. Although the readings are not that much high, but still there is a chance of some radiation induced things as well, so we have taken it into account.
Thank you.
Welcome, sir. Yes. Can I answer in Urdu? Yes. हम जितनी भी यहाँ पर स्टडीज जो मैंने इसमें शो की हैं, जिसमें मैंने कंपैरिजन किया है, इसका कोई एग्जैक्ट मेथडोलॉजी नहीं है। जितनी भी स्टडीज मैंने अपनी स्टडी को करने के लिए और इसको कंपेयर करने के लिए दूसरी स्टडीज से जो लोगों ने क्या किया, तो कोई methodology given नहीं है. There is no some TG guideline and another guideline. So it's totally up to you right now. You can consider it a volumetric source, you can consider it a line source, but we usually do, we consider it a point source. Point source की equation सबसे आसान है. You have to put the values and get the answer. Line source तो भी कोई नहीं जाता. So we have taken to another step. Any one of you can do it on another step. Go it for the volumetric as well, and that will be more good, obviously. But for the volumetric thing, as you can see here in this study, we have given only one dosimeter. Volumetric means you have to give dosimeter there, here, everywhere to the patient. This will be a more accurate study. Any other questions?
After this study, can you recommend any dose on which we can use the patient? Is there any recommendation dose rate on which?
Sir, it's basically written.
However, these doses are very less. That's very true. But suppose that you inject 15 mCi dose to a patient, immediately your student patient refuse to complete his or her scan. Then what will you release him, or what will be the criteria?
The release criteria is given in NRC 10 CFR. It's written here 760 MCI, and we usually do not give this high much dose in the diagnostic test. So related to only the patient release criteria, it will not be applicable to the diagnostic test. But it's a thing which we have given the radioactive source of the patient, so we won't let it go. First of all, there is a counseling of the patient before starting the test. So that's why in that stage, this all comes to an end. And if patient accepts for the test, it will be gone for the test, means it will be injected to the patient, but not that time. After the injection, we won't let it go.